This is a review of combinatorics for PS11, which should help count the number of microstates of a system and hence help in determining the entropy of systems. We start with the basic question, how many ways can we arrange n different items? So if we simply take n equals 3, as shown with these three numbered items below, we can start our ordering with any of the individual items. So if we choose 1, 2, or 3, then the next item that we choose could be any of the other two items that we haven't chosen from yet. So for example, if we chose 1 for the first item, we could choose either 2 or 3 for the second. Then the remaining item only has one possible choice. It's just the last item since we only had 3. If we want to count up the number of possible combinations we had, we just have to multiply the individual ones together. This is generalized to n different items, where we first have the option of choosing any of the n items, then we have the option of choosing any of the items that have not yet been chosen, which is represented as n minus 1, all the way down to the case where we just have one item left. Mathematically, this is defined as n factorial, which is n times n minus 1 all the way down to 1. A related question is how many ways we can put a certain number of items into a certain number of spaces that can be less than the number of items that we have to put in them. So if we take the same three items that we had before, but now only have 2 spaces to put them in, we can still start with any of the 3 items, and then we're left with any of the remaining items to put in the second slot. So we had 3 options for the first slot, 2 for the second, so we have overall 6 options. In general, for n items, we can choose n items for the first slot, n minus 1 for the second, all the way down to n minus k for the kth slot, which means we just multiply every number from n to n minus k. Mathematically, this is just the division of two permutations, n factorial divided by n minus k factorial, but it means the same thing as the graphic above illustrates. In the arrangements that we had before, we came up with several that represented the same arrangement, just in a different order, and I've highlighted them in different colors here. If order doesn't matter to the particular problem, then we only have a subset of the possible combinations that represent distinct choices. So, for this case, we have 3 duplicates, so without order mattering, we only have 3 different combinations. If we put n items in k unordered slots, we have the same picture as before, but we need to divide out any of the possible orderings of the k items, which is written as just dividing out k factorial for the k different slots. So we're taking the combinations that we had before and dividing out the permutations of k items to come up with the number of combinations when order doesn't matter. For a more concrete example, we can think of picking 10 courses to take over 2 semesters, where you take 5 courses each semester. We'll assume that you don't have to take the courses in any specific order, and the courses are available any semester you want to take them in. So we'll use this combination formula where it doesn't matter what order you take the courses in any individual semester. So we have n equals 10, k equals 5, and so n minus k also equals 5. If we solve this out, we get that there are 252 ways to arrange courses given this prescription. To even generalize further to when we want to divide things into not only 2 different slots, but 3, and even more, if we had 15 courses that we wanted to take over 3 semesters, we would still have n factorial in the numerator, but then we would have k1 factorial, k2 factorial, and n minus k1 minus k2 factorial in the denominator. All this means is we have n factorial different combinations to choose from, and we want to divide out any of the duplicates that occur from order mattering. So we take 15 to be n, and then each of the k's is just 5. Doing this, we see that there are 756,756 ways, which is significantly greater than our previous example, despite not really introducing many more courses. All of this is related to the concept of entropy because to calculate entropy, you need to count the number of states for a certain configuration. Entropy is given by Boltzmann's constant times the natural log of the number of microstates, so before you can calculate it, you have to know the number of microstates. And as we saw in the previous example, even when you have relatively small items to choose from, you can end up with a very large number of microstates.